Welcome back to the video lecture series on statistics for machine learning, and we are going through a very important portion of the probability, the theory of probability, and we were talking about the probability distribution functions, right? Now, we have already talked about the case of a discrete random variable where the probability distribution is known as the probability mass function, the function which represents this values at the different values of the random variable x. Now, note one thing, rather two things. One is this is a discrete probability distribution, just we saw about it. Now, since the number of possibilities or the number of possible values of the random variable x is finite, we can create such a distribution. And the characteristic of the distribution is, see, the sum total of the probability values for each of the random variables, values of the random variables, if we take the probability value and if we sum them up, it's always going to be 1 because we have all the exhaustive possibilities coming out here, right? So the total probability is going to be 1. Also, the other important point is fx is going to be always greater than or equal to 0. It cannot be negative. So that is one point. And second one is summation of fx is going to be 1 always, right? So this is one characteristic of a PMF, or a probability mass function. Now look at think about the situation when this random variable is a continuous random variable. Obviously, we cannot enlist the values of the random variable x in that kind of a case, because there can be infinite number, uncountably infinite number of values. So we cannot come up with a distribution like this, because if you really going to come up with a distribution like this, just think from a common sense perspective. There can be so many different possible values of the random variable. So the probability is going to be having a infinitesimally small value for each of the random variables, right? Or each of the values of the random variable. So you cannot create a distribution like this, right? So that's one thing we need to note about the continuous probability distribution. So how do we find that for a continuous probability distribution? So in continuous probability distribution, rather than having the value for a particular, this fx, rather than it representing the value of probability for a particular value of x, of the random variable x, what it does is it takes the value for a range of values. Say, for example, from x equal to a to x equal to b, the whole range of values, rather than taking one individual value. Because if you want to take one individual value, there will be infinite number of such values, and the probability values will be infinitesimally low, right? So that is one thing we have to keep in mind. And the way what should I say, the formulae pan out in case of a probability density function. This is called, in case of continuous random variable, instead of a probability mass function, what we have is called a probability density function, or simply a density function, right? So that is definitely one thing is fx is greater than or equal to 0. Obviously, the probability value cannot be negative. That is anywhere given. But instead of a summation, what we have to do is, since we are taking a range of values, here we have to do a, you have to do a integration. And what will be the integration? So it will be from negative infinity. So negative infinity to infinity. If we do a integration of fx dx, okay, fx dx, then that value obviously is going to be a 1, right? So instead of summation of fx equals 1, for PDF, what we can say is negative infinity to, integration over negative infinity to positive infinity, fx dx is equal to 1. And if you want to calculate a specific value of a probability, say for example, as we were talking about, so probability of x less than equal to a less than equal to b. How do we do that? Simple. I do an integration from a to b fx of dx. Okay. we will look at it more closely when we come to some of the very typical or very popular probability distributions or density functions, like a normal distribution, right? We will come into more details about this thing, but just I want to throw this concept for you. So basically what it resembles is, uh, if I think about fx, it's like a curve, right? We are talking about a polynomial, some kind of a polynomial which represents a particular curve. So a to b, integral a to b fx dx is basically nothing but the area under the curve from the starting point a to the ending point b, right? We will look more closely when we come to the specific probability distributions, okay? So I think that's these two are very important concepts that we all need to bear in mind. And these are going to be the foundational concepts when we go forward for the other things that we will cover in the subsequent lectures. Okay. So thank you very much. Stay tuned when till we come back. Bye.